Hi everyone, today we're talking about topic 5.6 and 5.7. The first is reaction energy profiles. So we've looked at these diagrams quite a bit before, but this is just a potential energy diagram that shows enthalpy. We've shown before that the difference between products and reactants in energy, that's delta H, and that tells you enthalpy. And you can find delta H by just taking the enthalpy of the products minus reactants. If it's negative, it's exothermic. If it's positive, it's endothermic. We've also discussed activation energy, which is the energy between the reactants and what we call the activated complex, or another word for this is the transition state. And it's the energy of this transition state which is dictated by kinetics, and the energy of that transition state that says whether or not a reaction is going to proceed or not, and also if a collision is successful. And in the next slide, I'll show what this kind of looks like in terms of a depiction. So here we have this very simple substitution where you take OH minus plus CH3Br. You make some sort of a transition state, which is somewhere in between them, and then you make CH3OH and Br minus, which are your products. So here, this is basically showing an exothermic reaction. Delta H here is less than 0. And you can see I have this initial reactant here, which has a C and 3 H's. These little white spheres are H's. And the Br is this red sphere here. I have my OH minus approaching in the correct orientation, and the transition state exists right at the top of that activation energy barrier. It's in between products and reactants, and it looks pretty much like both of them. You can see here, I have the C in the middle, I have the 3 H's from before, and the only thing that's changing is an OH minus or a Br right there. And then the products essentially look like that. That's the product I expect, and I get Br minus on its own. So the transition state is that one point right at the top of the activation energy barrier that is directly in the middle of reactants and products. And of course, you need enough energy to go past the transition state for a reaction to be successful. If you don't have enough energy, that reaction is not successful. Now that's a bit about it for 5.6. There's not much to it, and so we'll transition to 5.7, which is Introduction to Reaction Mechanisms. Now, a reaction mechanism is the sequence of elementary reactions that make up an overall reaction. We discussed this before, but if I have, for example, A makes B and B plus C makes D, right, my overall reaction here is that A plus C makes D because my B's cancel out. And this here, these two steps describe the reaction mechanism. In other words, these steps must occur in order to get the overall reaction. Now we also define a multi-step or complex reaction. This is basically just a reaction that occurs in two or more steps. And of course, you can use a reaction mechanism to describe these multi-step or complex reactions. Now, oftentimes, we'll take that previous little example that I have here to describe a reaction intermediate. And so let's say, again, I have A goes to B. That's one reaction. And in my second reaction, I have B plus C makes D, such that overall, the reaction is A plus C makes D. In this case, we call B a reaction intermediate. And a reaction intermediate is a chemical species that is created or made in one step, then consumed in another. It's important to note that, right, I make B in step 1 and I use B in step 2, but it does not show up in the overall reaction because it gets consumed in the overall reaction. We have this example here of cyclobutane. We make this activated complex. This is our intermediate. And then it breaks down to make ethylene. In the overall reaction, we don't have that activated complex, but it is made in the process of that reaction. And then finally, we've talked about rate determining step, but this is the slowest step in a reaction mechanism. And this determines the rate of reaction, which is why we call it rate determining. Now, we'll discuss intermediates quite a bit, and there's going to be a lot of questions dealing with this on AP Classroom. But an intermediate is not a reactant or product. If we look here at our energy diagram, our reactants are here on the left, our products are here on the right. It is also not the transition state. An important thing to note here is that the transition state, which I'm going to label TS, cannot be isolated and is not stable. In other words, you can't actually make it. It doesn't actually exist. It's just a state that's right in the middle of your reaction. An intermediate can be isolated and can be stable. So in an energy diagram, the intermediates, I'll label I, are in this little valley. So you'll have reactants pass some sort of transition state where you need a particular amount of activation energy. Then they'll rest in this little valley that's a little bit stable before going to a different transition state, and then finally ending at the products. And so in some instances, you can isolate an intermediate. So we've seen this example in class before, but let's say we have this reaction here where in the first step, we have 2NO2. We'll make NO plus NO3. That's our slow step, otherwise known as the rate determining step, or RDS. In step 2, we have NO3 plus CO gets turned into NO2 plus CO2. Now, we know that we can add these reactions together to get an overall reaction. And since we see NO3 on both sides, our overall reaction essentially cancels those out. And we also have some NO2 at the start as well as the end. And so I end up getting NO2 plus CO makes NO plus CO2. These NO3s here, in step 1, you make NO3, and then in step 2, you consume NO3. This essentially makes NO3 an intermediate, because in the first step it's made, and in the second step it's immediately consumed. Now, there's a similar concept to an intermediate, and that is known as a catalyst. And we've learned about this in the context of activation energy. But what a catalyst does is it lowers activation energy needed for a reaction. That's one definition, but there's an important other caveat to that, which is that a catalyst is used in the first step of the reaction, then reformed in the last step of the reaction. So an example of this is as follows. Let's say in step 1, I have Cl plus O3 react to form ClO plus O2. In the second step of my reaction, I have that same ClO plus another molecule of O will react together to reform the Cl and make O2. Now, my Cl is used up at the start to make some sort of intermediate. That same intermediate is then immediately consumed to reform my Cl. Now, if I make my overall reactions and add these together, what we'll notice here is that the Cl's cancel out and the ClO's cancel out because they're present both at the start and the end. So my overall reaction is O3 plus O react together to make 2O2. My intermediate is ClO, and my catalyst is Cl. And so with this, we can write basically a scaffold for a reaction mechanism, or basically some rules. And those will be here. And for any time you're writing a reaction mechanism or looking at one, they should always fulfill all of these rules. The first is that the rate law must be determined by the slow step, otherwise known as the rate determining step. That is rule number one. Rule number two is stoichiometry must be obtained when steps are added up. This is essentially Hess's law, right? You need to make sure the stoichiometry is right. Rule number three, each step must be balanced. Again, going back to Hess's law, you must balance all your steps so that when you add them up, all of your steps will equal the overall reaction. Number four is that all intermediates are made, then immediately consumed. So in one step, you must make the intermediate, and the next one, you must consume that intermediate. The last is that any catalyst is consumed, then reformed. So you can think of intermediates and catalysts as essentially being opposites in terms of reaction mechanisms. Of course, intermediates are isolated in the middle of a reaction, where catalysts serve to lower the activation energy, but those are first consumed, then regenerated. We'll go over some practice problems in class, but for now, that's all. Thanks, guys.